Hello everyone, this is going to be section 10.3 on tree and rooted trees. So first let's go to the definition of what is a tree. First, let's start with the notion of a circuit-free graph. Of course, as you can think, a circuit-free graph is just going to be a graph that contains no circuits. In particular, a tree is going to be a graph that is going to be circuit-free and is going to be connected. In opposition, a forest is a circuit-free graph that is not connected. So it's going to be like a disjoint collection of trees. Now, let's see an example here of a tree. You can see a bunch of different nodes. One of them is what we consider the root, and then they start branching out. As you can see, they're connected, but they have no circuits. In opposition, this is not a tree, because it contains a circuit. Now, in a tree with two or more vertices, a leaf or terminal vertex is going to have degree 1. An internal vertex or branch vertex has degree bigger than 1. So for example here, this is a leaf and this is an internal vertex because it has degree bigger than 1. This is a leaf because it has degree 1. Now, one of the theorems is the n-1 edge theorem to define a tree, and is that any tree with n vertices is going to have n-1 edges. The converse of this is that a connected graph with n vertices and n-1 edges is going to be a tree. Some quick example of that will be a graph with 10 vertices and 12 edges is not a tree, because a tree with 10 vertices needs to have exactly 9 edges. Also, a graph with 5 vertices and 4 edges that is not a tree must be disconnected. It's the only reason why it will not be a tree. They need to be isolated components. Now, commonly, we're going to be interested now in showcasing some of the uses of tree before we really go into deep doing examples. And is the uses of trees, they can be used for operations in programming, but they can also use as decision trees. So for example, a decision tree is going to be a rooted tree where each of the internal vertex is going to represent a task or decision, and each of the branches is going to give you an outcome. The leaves hold the final conclusions at the end. So for example here, a math placement exam. On the first part, we verify certain conditions. For example, if you got in part 1 less than 6, then you get 100. If you got bigger than 8, then in part 2, you got, let's say, bigger than 10, then you have 120 points. If you got less than 10, then you can get 110. If for part 2, you got between 6 and 7 points, then in part 2, if you get bigger than 6, you're going to get 110. And if you get less than 6 points, then you're going to have around 100. Okay? So as you can see, the transition between the roots and the internal nodes depends of holding certain condition. Here is we transition to the left side if it's bigger than 8, the score in the part 1. And if it's less than 6, then we go to the right side. Then also, if we're between 6 and 7, then we're going down this path. So the decision tree depends on the conditions that you're given in each of these steps. Each of the path roof, the leaves is going to encode one sequence of decisions that's going to be next. Now, the rooted trees is a tree with a designated root for a vertex. We define some of the important things here, like the level of the node B, which is going to give me the number of edges from the root to that particular node B. The height of the tree, which is the maximum level of any vertex. The children's of B, which is the adjacent vertices one level lower of that node B. The parent of B, which is the adjacent vertex one level higher. And the siblings, which are vertices sharing the same parent. So for example here, we have the root, which is the level 0. Level 1 will be this 2. And finally, the leaves will be this. Notice that this is a tree of height 2. The two dark nodes are going to be the siblings, and the children's of the roots are this two. And then finally, from these two, their children's are going to be what we call the leaves. Now, we can transition to n-array trees and binary trees. In n-array trees, every parent has at most n children. In a binary tree, we're talking about n equals 2. So each child is additionally labeled left or right. In a full binary tree, every parent is going to have exactly 2 children. Now, when we have binary trees, we can do full binary tree counts. And a full binary tree with k internal vertices is going to have 2k plus 1 total vertices, and it's going to have k plus 1 leaves. We have a theorem to determine the height of the tree, or the height bound, really, of the tree. So a binary tree with height h has at most 2 power to the h leaves. So this is going to give me the maximum that goes. Okay? So because of that, we have this inequality here where t is less than 2 to the h, or we can actually say that h is the roof of log of 2 of the number t. Notice that for a binary tree cannot have height 2 and 38 leaves, since pretty much 2 to the 5 is 32, which is going to be less than 38. The minimum height needed for 38 leaves is going to be 6. So this is pretty much telling me how much leaves are possible for a tree of a particular height. Now, binary trees we can define for algebraic operations where the internal vertices are going to be operators and the leaves are going to be the operands. And the operator at each vertex adds on his left and his right to trees. So, for example, here, this expression a minus b times c parenthesis plus division between d and e. So notice that the last terms, the numbers, are going to be the last possible leaves, and each of the signs is one interaction that is going to be recorded in one of the internal vertices. So for example, a minus b is a minus b. Then, because we're doing it times c, then we have this times c. Then we have the operation plus here in the middle of the root. And then we have here on the other side, we have d divided e with this sequence and adding up to this. So notice that this arrangement pretty much has a particular ordering where we're having some of the operations on the left side, some of the operations on the right side, and certain operations are going to be the root of the entire thing. So for example, the most dominant operation here, which is the plus between two sides of the operations, is going to end up being the root node. Now this particular tree has 4 internal vertices and is a full binary tree with 4 plus 1 equals 5 leaves. As you can see here, A, B, C, D, and E. Those are going to be the final leaves. Now, but in particular with these trees, we have different ways that we can arrangement to go. And that's what we call a tree traversal. So a traversal visits every vertex exactly once. And we have 3 standard recursive orders for binary trees. So we can go with the pre-order, the in-order, and the post-order. So the order for the pre-order is pretty much we start with the roof, we go to the left, and then we go to the right. The pattern is also summarized as NLR. The in order is going to be the left, the root, and the right. So this N is making it for the root node. Okay. In the post order, we have left, right, and root. And so that's going to change a lot of how we represent a particular set of operations. We're going to look at that like with the previous example. But the memory here is in the pre-order, the roots go before the children. And the post-order, the root goes after the children. And then the in root, it goes between the children. So you can kind of see that we have here. This was an in order tree situation because the root was between the children's. Now, traversal is going to be recursive. So for each of trees, we're going to apply the same rule starting at the root. So for example, some traversal examples here, we have the node A, B, C, D, E, F, and G. And so the pre-order, we start from the node, then we go from the left and then from the right. So we start from the node A, from the root, then we go to B, then we go to D, and then to E. Okay, that's the left side. Then we go to the right side, C, F, G, and we'll go from left to right. Now, in order, the traversal is going first by the left, then by the root node, and then on the right. So we're pretty much going D, B, E. We start by the left side most. We go back here to this root node, then we go to this, then we go to the root node, and then we transition to the other side. We go with F, C, G. Now, the post order, we're doing left, right, and then the root node. So we have, once again, the DEV. This is one way to go about it. And then we have F, G, C. Notice that in this post order, we're going first over the leaves, and then we transition to the next level. So that's why we have DE, and then we go to B. And here we have FG, and then we go to C. And then finally, we go to the root node, which is A. In ordered traversal of a binary tree search is always going to be producing keys in sorted order. And each traversal of an expression is just going to yield a different notation. For example, if we think about the results for the A minus B times C plus D over E that we see before, the pre-order is going to give us things like the signs are going to go first. So we're going to have first the root node, then we're going to have the parents nodes, and then we're going to have the leaves. And that's going to be the order that we have those things in there. Now, in order is a similar thing. Here, of course, it will be very useful to have a parenthesis, but this is how the computer will interpret this type of order when you're doing traversal. Okay. Similarly, with the post order, notice that the root is at the very end. So that's the way that this is going to be interpreted from the computer point of view according to the traversal that you're picking. Now, why the postfix, the RPN, matters in computing? For the most part, the postfix is unambiguous without parentheses. It's not going to need parentheses to separate things and to make an evaluation from left to right. So this is mostly used in calculators and compilers, in particular in comparison with the others that might need the expression in parentheses to actually get the right result. Okay, so in summary, we learned a concept that is going to be very used in computation, the concept of tree, with the notion of being connected circuit-free. And if we have n vertices, it needs to have n minus 1 edges. The rooted tree is designated for levels, height, and we're analyzing parent-child and sibling relationships. We have the inary and binary trees, which are pretty much dependent on how many children's per parent the tree is going to have. Binary is just going to add left and right distinction. If full binary is just going to be exactly two children per node. The full binary tree with k internal vertices is going to be having 2k plus 1 vertices, k plus 1 leaves. And in general, for an age height tree, we're going to always have that that's going to be less than 2 to the h leaps. Now, a traversal is something that we can use to visit nodes in particular. So we always go with pre, in, and post order. And they visit all the nodes, but the order depends of how you're doing things. So um, you can have a sorted order of sorts, and the post order expression like the RPN is one of the most used in computations. Now, for applications, we use this for decision trees and parse trees, binary search trees, and those are going to be part of the algorithms that are built in categorizing things. Now, we want to be careful not to confuse forest with trees. You got to remember that forest is disconnected while tree is connected. You want to be careful with not misapplying the n-1 edge theorem. The n-1 is about edges, and with n vertices, that alone does not guarantee a tree. It must also be connected. Disconnected graph can have similar conditions. Now, when you're getting the traversal, you gotta make sure that you know where your root node is going. So, for example, you have this NLR, LNR, and LRN, and the N is always representing where the root is. The name is always telling you where the root is visited relative to its children. Now, it's always important to not to confuse full versus complete binary trees. In a full binary tree, every parent has exactly two children, but in a complete, all levels full, except with possibly the last, are filled left to right, and those are different concepts. Okay, so make sure now that we're introducing the basic notions, make sure that you take a look at the examples, since here we're going to enter in depth in a lot more on how to deal with all these particular concepts. Okay, see you on the examples.